Alright, welcome to another video on electric circuits. Today we're going to be talking about something that is very fundamental, and it is called Kirchhoff's laws. And sometimes it is pronounced Kirchhoff, but it's really just a way of pronouncing this. It is a German surname, so the correct pronunciation is actually Kirchhoff. But either way is fine. I mean, people tend to use both interchangeably, and I think at this point people know what you're talking about when you pronounce it either Kirchhoff or Kirchhoff. So it's up to you to decide how you want to pronounce it. Now, there are two laws that essentially tell us how things work in an electric circuit. One of them is Kirchhoff's current law, or KCL, which says that when you have a node or a connection between different wires in a circuit, the currents coming in and out of the wire should basically add up to zero. So what this is saying is that the currents coming in, or the sum of the currents coming in, should be equal to the sum of the currents coming out. Now, this is not a very surprising result because we know that current is essentially just the flow of electrons. So by conservation of mass, we know that there has to be conservation of charge, and as a result, anything that comes into the node must also come out, otherwise we're basically violating the laws of physics. So this is a very, very important concept that is very useful in analyzing circuits, and we're going to see how we can apply that in different situations. So essentially, in short, we just represent this by the sum of the currents coming into a certain node. The K, the subscript, represents which of the currents we're taking, and that should be equal to zero. Normally, we need to choose a convention, so what I like to do is whatever is coming in, I treat as a positive current, and whatever is coming out, I treat as a negative, but you can choose whichever you want as long as you're consistent. The next thing is Kirchhoff's voltage law, or KVL, which says that in any closed loop circuit like this, you're essentially going to have a current that is going to go around, and the sum of the potential differences, so across every component, it could be a resistor, a capacitor, inductor, whatever, the sum of those voltage drops should essentially be equal to zero. So in any closed loop, this should actually be the case, and this is another very important result. Now let's see how we can apply this to analyze some circuits. So let's say that we want to find the total current flowing through this circuit. And let's say, because I know that in high school you learned that when you have a bunch of resistors in series, you can just add them up to make an equivalent resistance. But let's assume that we didn't know that. The only thing we know in terms of electric circuits is just these two laws. So let's see how we can apply that to find the current. We have a voltage supply, DC voltage supply is 10 volts, and essentially that means that the current is going to be flowing from the positive terminal to the negative terminal, just like that. Usually, when you have a voltage drop across a resistor, since this is the positive end, then this would be the positive terminal of that resistor, and that would be the negative terminal. So it essentially is saying that the voltage is decreasing in this direction, and the same applies to each of these. So normally, the convention should always be like that. So if the current is going like that, we are essentially going to describe it in these terms. Now, we know that by Ohm's law, the voltage is related to current via each of the resistances, so we can easily find what the voltage drop is going to be across each resistor. So we're going to start off with the first one over here. So we know that by KVL, the sum of the voltage across this closed loop should be zero. And then we're going to, since this is the power supply, we're going to treat that as positive voltage, so that's going to be 10 volts. And now everything else, you'll notice in this case, the current is going in this direction, so it is going from negative to positive, so we treat that as positive convention. But here the current is flowing through from positive to negative terminal, so that we're going to treat that as negative. Okay, so essentially we're going to have 10 minus 1 times I. So we're essentially applying Ohm's law in there. Then for this one, we're going to have minus 2I. And then the last one is going to be minus 1I again. So we're going to add up all of those. 0 equals 10 minus 4I. Now we move this to the other side, and we're going to have I equals to 10 divided by 4. Now remember, this is in volts, this is in kilo ohms. So the answer that we get is going to be in milliamps. So 10 divided by 4 is 2.5, so that's 2.5 milliamps. And we could actually check that this is indeed the case, because we could just find the equivalent resistance of the circuit, So we have 10 volts over here, and the equivalent resistance would be, since all the resistors are in series, it would just be 4 kilo ohms, which means that if we were to find the current, we could just find it directly from V divided by R. And in this case, we know that's going to be 10 divided by 4, which is once again 2.5 milliamps. So it turns out that these rules of adding resistances to basically calculate an equivalent resistance, whether it's in series or parallel, comes from Kirchhoff's laws. And that's a very important concept that we need to keep in mind. Now let's apply KCL to analyze another circuit. Suppose we have something like this. Let's have a DC voltage supply again. Now let's make it 5 volts. Let's have a resistor over here, maybe another one over here, and then I would say let's have another one over here, just like that. So let's make this 2 kilo ohms, 1 and 3. Okay. Now the first thing we could do in here is, well, we could just combine these two, right, just to find out what the voltage is going to be across each of these. But essentially what we want to do is we want to find out what the current is across each of these resistors. So we're going to call this one I1, this one I2, and we know that because charge must be conserved, if this is what is coming in, then it must come out in this direction as well. And we're going to call that I3. So we're going to be looking at this single node, just like that. So we have I2, this is going to be I1, and I3. Okay? Now, what is I1 going to be? Well, I1 is essentially going to be the total current going through the circuit. So in order to find that, we could find the equivalent resistance. Now, when you're adding resistors in parallel, we essentially say the total resistance, or the reciprocal of that, is equal to the sum. And let me just write this in a better kind of format here. The sum of the resistances in parallel. So essentially we could say that the total resistance over here, or essentially let's call it R2 parallel R3, is going to be equal to, we put this on that side and divide by the other, so it's just going to be 1 over R2 plus 1 over R3, and that's going to be 2 to the power of minus 1. Okay, so in this case R2 is the one that is over here, so that's going to be 1 divided by 1, and that's going to be 1 over 3 minus 1. And now we're going to plug this in a calculator to see what we get. And this is essentially going to give us 0.75 kilo ohms of resistance. So that's basically what we're going to get there. And now if we add it to this extra one, then the equivalent resistance for the whole circuit is going to be 2 plus 0.75, which is 2.75 kilo ohms. And now with that, what we can do is we can calculate the current 1, which is going to be equal to the total current for the circuit, and that's going to be the voltage divided by RE. So that's 5 divided by 2.75. So let's see, 5 divided by 2.75, that's about 1.82 milliamps. I have rounded up to 2 decimal places, but it is very close to this value. And with that, what we can do is we can say, okay, so now that we have that, we can find out what I2 and I3 are going to be. So let's go and do that. So I1 should be equal to I2 plus I3. And the main reason, this one is the one coming in, these two are coming out. So we know that 1.82 is going to be equal to I2 plus I3. Okay. Now obviously we still have two unknowns, so we want to know exactly how we're going to find that. Now in order to find that, what we could do is we could say, okay, so let's find the potential drop across each of these resistors. So one way in which we can do that is to use, we have the total current, so let's draw the circuit like this. So we have 5 volts, coming in this way. Now this is 2 kilo ohms. This is the equivalent resistance of the two resistors in parallel. And now in order to find, that's the total current, in order to find the potential drop across this, which would be the same potential across both of those resistors, we're essentially going to have to just use Ohm's law again. So the potential drop across this one is going to be equal to total current, which is 1.82 times 0.75. So 1.82 times 0.75, and that's going to be 1.365 volts. Remember, that's milliamps times kilo ohms, which gives us units of volts. And we could check that this adds up to 5 volts by finding the potential difference across the 2 kilo ohm resistor. So 1.82 times 2, which is going to be 3.64. Now, because I rounded this up, you notice that the addition of these two is going to be slightly over 5 volts, but that's fine because we know that we had to round this up because it has a recurring decimal. So it does indeed check out, so we know our calculation is correct. Now that we know the potential drop across each of these, we can find I2 and I3. So I2 is going to be equal to this potential drop, 1.365, divided by the resistance over here, which is 1. So that turns out to be 1.365 milliamps, and then I3 is going to be equal to this same potential drop divided by the resistance, which is 3. And when we plug that in our calculators, that's going to give us about 0.455 milliamps. So now if we add these two together, we should get something close to 1.82. So let's see if that's indeed the case. Plus 0.455, and indeed we do get 1.82 milliamps. Okay, so we know that our calculators are correct. And this is essentially how you use KVL and KCL. In fact, we're going to be using this in pretty much any circuit that we analyze in this video series. So recommend that you really remember these rules because they apply to pretty much any circuit you want to analyze, and they're quite useful for deriving even more sophisticated rules and shortcuts for analyzing circuits.